In this video, let us understand how do we calculate and verify for the transient and steady state analysis for a given RL and RC circuit. So I am Mohan BS, working as assistant professor in Department of EEE SJBIT. So transient state refers to the short period of time immediately after the circuit is energized either by the applied current or voltage. So during this period, the circuit's voltage and currents are changing, that is across capacitance and through inductance, from their initial values to their final steady state values. So let's plot a graph with respect to time, and here let us see how the current changes through an inductance. So this is V by R, that is nothing but current. Let us say we have a 1 amp of current. So this is the curve, right? When the circuit is being energized, it takes some amount of time for charging and then it remains under steady state. So this line, you can see it matches with our steady state value, that is it remains constant. Thus we can say that this highlighted color is actually under steady state. So initially the circuit behaves under transient condition, or it is under transient response, and it is constant. The value of the current remains constant from this particular time and hence and thereafter, and that period is called a steady state response. So this shaded area is called transient response. So transient response is given by the equation I is equal to minus V by R E minus R by L T plus V by R for steady state response. So this is the complete response for the current, which includes transient as well as steady state response. Further simplified, I is equal to V by R 1 minus e power minus t by tau, where tau is called as your time constant, which is given as L by R. That is the time taken for charging through inductance or charging across the voltage, charging voltage for your capacitance. Whereas for capacitance, the tau is given as R into C. So here for with respect to voltage, for capacitance, the transient response of voltage is given as 1 by S or V naught. Sorry, it is V naught 1 minus E minus T by tau, where tau here is R by C. So in numericals you will see what exactly are these resistance, okay, and the further analysis. So this is just in brief to understand what exactly is transients, and let us understand these switching cases shortly. So let's take this example here to understand the switching cases. So you can see here the tail is at position 1 and the arrow is moving away from position 1. That means the earlier position of the switch is at 1. So we call that earlier position as t is equal to 0 minus, or t less than equal to 0 minus. Okay, and you can see after we energize the circuit, the switch is moved to position 2. The switch is moved to positions 2. It is represented as t is equal to 0 plus. That's after it's being energized. So when the switch being energized, it is energized at t is equal to 0. So similarly here the tail is at this end, the arrow head is at this end. That means the initial position of the switch is actually closed. That is t is equal to 0 minus, it is closed, and 0 plus it is being opened. So giving this as a reference, so you can see now the tail is here, the arrowhead is here. So 0 minus, it is closed, 0 plus it is open, and it is operated at t is equal to 0. Let's take one more example. So here the tail is at this end and the arrowhead is at this end. So you can see that the switch moves from this position to this position. That means it is being opened and then it is getting closed. It is getting closed here. Initially it is at open position, and at when the circuit is being energized, it is getting closed. Similarly here the switch, the tail is here, the arrowhead is on the other side. So that means initially it is being opened, and then when it is energized, the switch is getting closed. So this is how one can analyze for the switching condition, that is what is the position of the switch initially. In generally they would mention in the question, however it's better you analyze in this order also. The position of the switch at t0 minus and t0 plus. So what is 0 minus? So 0 minus is nothing but the position of the switch initially what is the position of the switch before we energize. And when do we energize? At t is equal to 0 we energize, And after we energize, what is the position of the switch? That's given as t is equal to 0 plus. So initial and final values, we have derivations to be done. So I'm just concluding so that you understand the numerical. So if there is no current flowing, when you're solving, let's say you take this problem and we are solving, when there is no current flowing through the inductance at this position. Now here, what is the position of the switch? The position of the switch is closed. So when the circuit is closed, when we solve the problem for the current through the inductance at t is equal to 0 minus, and if there is no current, when we find out that at 0 minus there is no current, we represent the inductance at t plus as open circuit. If solving at t is equal to 0 minus, if we find there is some current, let us say that we have 1 ampere, so we represent that current as it is at t is equal to 0 plus with the same orientation. That is, if the current is going down with 1 ampere, we represent that as 1 ampere. If the current is going up with respect to 1 ampere, we represent in that orientation at t is equal to 0 plus. So these are initial conditions in elements for inductance. So what are the final conditions? So the final conditions, under steady state there is no change of current. Thus voltage can be represented, voltage across inductance is given as V is equal to di by L di by dt. As L di by dt is 0, voltage appears to 0, thus voltage is 0. When do we for inductance voltage 0 means inductance act as short circuit. So voltage 0, how do we represent voltage 0? We just represent it by a short line. So similarly, the initial conditions of for this case, since we had current, so how do we represent that condition? Also by short circuit. As you can see here, we create a small loop here. So these are the initial and final conditions for inductance. So let's see initial conditions for capacitance. Now, if let us say solving, if we find out that there is no voltage across this capacitance, its initial condition. So what is the initial condition? This itself is the initial condition, right? So at this position of the switch, if there is no voltage, that is V is equal to 0, how do we represent 0 voltage? Just by short circuit. If we find out that yes, we have around 10 volts, just a vague example, if we have a 10 volts at t is equal to 0 minus, then we represent that with the same voltage magnitude and its orientation. That is, here it's being plus and here it's being minus. So these are initial conditions for capacitance. Now what about final conditions? So final conditions, there is no, under steady state condition, there will be no change in voltage across capacitance, there will be no change in current through inductance. In this case, there is no change in voltage across capacitance. Thus I is given as C dV by dt, that is current goes to 0. When do we represent current 0? How do we represent current 0? By open circuit. So thus t at infinite or at final condition, we represent capacitance as open circuit, right? That means under steady state condition, inductance is represented as short circuit. Under steady state condition, capacitance is represented as open circuit. I repeat again, under steady state, inductance as short circuit. Under steady state, capacitance as open circuit.
So figure A, we have to find voltage at three conditions, and when time is 0 minus, 0 plus and 200 milliseconds. That is, when the switch is closed, switch is just opened, and once it's opened, after 200 milliseconds, what is the voltage across your resistance? So we can divide the circuit in two different ways. That is, the switch, the initial condition of the switch and the final condition of switch. That is, as shown in figure A, we have a switch when it is closed. So the switch is initially closed as shown in figure A, that is represented as less than 0, and figure B, at t is equal to 0 we are opening the switch, thus it is an open circuit, and we have a source free circuit for t greater than 0 as shown in figure B. So let's solve for figure A to find what is the voltage at t is equal to 0 minus. But let's find out what is IL. So I'm sure the answer for V, voltage across resistance, for t less than 0 is 24 volt. But let's find current, and why we'll see in the upcoming slide. So we are solving for IL for t less than 0, that is t is equal to 0 minus. But how does an inductor act in a DC circuit? It always acts as short circuit, as we know XL is equal to omega L, and omega in DC circuit is 0. Now, so best by Ohm's law, we can find the current, that is 2.4 amperes. So thus we can say that the change, as we have seen in the derivation, that there is no the change across the change through in the current through inductance does not change instantaneously. Thus we can say IL of 0 minus is equal to 2.4 amperes. Now, why do we find this? We know a generalized equation for I of L of t is given as I naught e power minus t by tau. Now, when we want to find a t0, right, or t0 plus or t greater than 0, the same formula is applicable. However, we have to substitute t as 0 to find out your value. And similarly, solving for tau, we can also substitute t as 200 milliseconds and then find out the current through inductance at any time. So for both conditions, you can see we need I naught. What is I naught? The value of current through inductance before the switching action. That value of current is 2.4 amperes, and that's the only reason why we've already solved for IL0 minus, right? So IL0 minus is nothing but I naught, that's 2.4 amperes. Now let's solve for t greater than 0, that is t0 plus. So as known, t greater than 0 or t is equal to 0 plus, the switch has come to action. That is, the switch is opened, thus we have a source free circuit. So from this circuit one has to find what is your time constant, that is L by R equivalent. And R equivalent across your 5 Henry is 10 and 40 ohm are in series, thus it is 5 by 50, that's 1 by 10 seconds. Thus substitute the tau as 1 by 10, it comes as minus 10 power minus 10 t. So voltage equation is given as minus 40 into IL of t for t greater than 0. So once you substitute the value of IL and substitute the value of t as 0, you get the answer as minus 96 volt. Substitute t as 200 milliseconds instead of 0, you get the voltage as minus 12.992 volt. Thus these three are what is being asked, that is V is equal to 24, V is equal to minus 96, V is equal to 12.992 for t 0 minus, 0 plus, and t is equal to 200 milliseconds respectively. So these are your answers. So let's move on to simulation. Right? So the components required for 10A, we need one VDC, we need two resistance, we need one inductance, and we need one switch. So what is the final condition of the switch? The final condition or the initial condition is actually closed. The final condition is open. Thus we need SWT open. The switch open is what we need, and we need one common ground. So let's go to simulation. So we need ST open. So let's rotate them and place accordingly. We need two resistances. So let us rotate one. Yes, and then we need one VDC. We need one inductance. We need one common ground. Let us zoom in. Let us value them. So this value is 40. This is 24. This is 10 ohm. And the value of L is given as 5 Henry. Now let us connect one by one and build the circuit as per the diagram. Now if you observe, I have created a shortcut here. So we have to delete this wire. Now where you have to find voltage? We need to find voltage across 40 ohm. So go to markers, mark voltage differential. So top it's positive and at the bottom it is negative. Now go to setup analysis, enable transients, and the print time is 0 and the final time should be slightly greater than the time that we have used. We have used 200 milliseconds as a time, so let's set the time as 250 milliseconds. Save the file. So let's simulate. So as you can see, the result we're getting, as we click on toggle cursor, we're getting the voltage as 23.97 whereas we've got the voltage as 24, and the time is equal to 0 plus. So let's see. So you can see here, so this is the peak value of cursor, this is cursor trough, and the value is minus 95.875. just when we have opened the switch, the value of voltage has reduced to minus 96 voltage, and then we need to find what is the voltage at 200 milliseconds. So go to cursor search, and what value we must find? We must find time, and time is it on x-axis or y-axis. As you can observe, the value of time is on x-axis, so we use the code SFXV, that is search for the x value 200 m, and remember to type small m, and as you click enter, you can see here A1 cursor landed at 200 milliseconds and the value is 12.974. But I think you have already observed that the values are not matching, right? We have got 24, we have got slightly lesser, we have got minus 96 in theoretical calculations, and we got it slightly lesser. And here again at time is equal to 200 milliseconds, we have calculated and the answer is minus 12.992, but whereas in simulation we are getting 9.97. So why is this difference? So let's go back to the simulation. Now just kindly observe, I'll change the resistance when the switch is closed. So here when the switch is closed, I will reduce the resistance further, and when the switch is open, I'll try to increase the resistance, right? And now let us try to simulate and check, do we get the same answer or we get the answers somewhat near to our calculations. Click on toggle cursor now, and you can see we're getting the answers exactly to what we had calculated. That is 24 volts. So cursor trough minus 96, go to cursor search and type the code search for x value 200 m. we are getting minus 12.992, but we here in simulation we are getting minus 12.991 volt. Thus 10.8 is very calculated and verified in PSpice. Now let's see a second problem in the same experiment to find voltage across capacitance at t less than 0 and greater than 0, as well as at a t 160 microseconds. So this is an source free RC circuit. So let's see how do we solve. So again we can divide this as two figures. For figure A, less than 0, figure B, greater than 0, that is when the switch is being to action. So from first figure we can apply, we can see that the capacitance behaves as open circuit always in DC circuit. We know Xc is equal to 1 by omega C. As omega is 0, we get Xc is equal to 1 by 0, which is nothing but infinite, and thus we are replacing capacitance as open circuit. Now I can simply say that V of 0 minus, when we analyze, I get the value as 50 volt, as the current is not passing through 70 ohm. Why? Because the circuit is open. Thus the voltage across capacitance, or V, is equal to 50 volt. It is plus 50. Why? Because this positive is connected to this positive and the negative is connected to this negative. Thus it is 50 volt. Now let's see what is T0 plus as well as 160 microseconds. So in series RC circuit, as we are aware, V of t is equal to V naught e power minus T by RC, where RC is your time constant. So RC is equal to 80 into 2 microseconds, right? So what is the value of R? The value of R is nothing but, as we did for RL circuit, the value of R that is parallel to your capacitance here, right? So V0 would be equal to 50 volt. Now, but we have to find a t is equal to 160 microsecond. Substitute in this equation. I repeat, substitute in this equation the value of t as 160 microseconds, and then we get the answer as 18.394 volt. So these are the answers that we must verify. That V is equal to 0 negative as 50, 0 plus is also 50, and at any time greater than 0 we get the answer as 18.394 volt. Now let's see how do we do simulation for the given circuit. I have connected the circuit diagram, but we know that we need two switches here. So let's see the now required. So the components required are the same as what we did for figure A, but we require two switches. We do not have a one switch which shifts us on the other side automatically, right? So because of that we take two switches here, right? So you can see here, as the switch opens, at the same time this switch closes here, right? So this is done to match the circuit diagram as shown, right? So that's all is what you must do here, and then let us revalue them so that we get the answers accurate. So let us reduce this by further value, and let us increase 1 mega to 2000 mega. So I have placed a voltage marker. Go to setup analysis, enable transient, and transient, the value of final time should be slightly greater than what we have set. We have set 160 U, that is 160 micro, so I have set here as 200 micro. So let's simulate and see if the answers are matching. Compare our answers now. So this is your output. Let's delete the old file. Yes. So click on toggle cursor. You can see the value as 50. Right? And then let us click on cursor search for the value SFXV 160U. And the answer is 18.454. Right? So slightly greater, or we can round it up and say it's 18.4. Right? So this is how one has to calculate and simulate your results in PSpice.
So remember, the circuit must be inspected by lab instructor or faculty before you energize any hardware experiments in laboratory. So thank you for watching the video. So please do subscribe the channel to enhance your learning curve.